Hi guys, welcome to Chem 223. My name is Dr. Mortensen. Okay. First off, let's talk about me and my family. This is a picture of me and my family in front of our house. This obviously is me up in top, my beautiful wife Lisa, and our three kids, Violet, Chloe, and Peter. And then last year we decided, you know what, let's go for one more. And we had little baby Cynthia, and she's adorable, and she smiles. She's got really chubby hips, and it's really cute. And then, of course, we've got our two puppies, Belle and Luna. And this is our family. Everyone has aged a little bit since these pictures were taken. This was taken when Belle and Luna were, I think, 8 or 9 months old. They're now a year and a half, so they're a little bit bigger. Cynthia here is now about 6 months old. Beyond my family, I enjoy writing science fiction and fantasy novels for fun. Both of these two are on Amazon right now, selling like hotcakes. And by that I mean I've gotten a few of my family members to download them. Now in Chem 223, I like to start the class off by introducing a motto. And the class motto is, "Put on the name of Jesus Christ." So hopefully, through me sharing my testimony throughout this semester, you'll be able to develop a stronger relationship with Christ, and hopefully you'll take some responsibility on yourself to develop that relationship as well. The learning objectives for this class are: 1, to gain an understanding of statistical data analysis. That'll be your favorite part of the class, I'm sure. The second part is to learn current best practices in analytical chemistry. And 3, become better at critically analyzing scientific results. So that first segment of this video was recorded last spring. Most of the lectures you're going to be watching this semester were actually recorded last spring. They should be good enough for us, but if you run into any issues, if I get anything a little mixed up, please let me know. So the structure of the class this semester is going to be as follows. You will have lectures associated with Monday and Wednesday. Those are the days we'd normally have in-person class. These are asynchronous lectures, so they're always just going to be a video just like this one that you'll watch by yourself. If you'd like to get ahead, you are free to do that. There will be about 2 homework assignments a week, 1 associated with each hour of lecture. Labs will be in person Monday and Wednesday from 2 to 5. And I will assign you lab stations when you get in there. This class will have 3 exams. So let's go over all of these things in detail. Like I said, we have a lecture associated with every Monday and Wednesday. Of course, that excludes holidays and days off. The lectures are slightly out of order. This is because right now we're planning to go completely online after Thanksgiving. And I've had to rearrange some of the labs because of this, and so I've rearranged some of the lectures as well. This shouldn't be a big problem. Everything should run smoothly, but if I did forget something in the reading or in the videos that completely doesn't make sense, feel free to let me know, and then I will try and correct that for the whole class. Each lecture does have reading associated with it. That reading is in Exploring Chemical Analysis, 5th edition by Daniel Harris. The reading assignments are listed on Learning Suite, and I will show you those in a second. For every online lecture and reading assignment, there is a quiz also on Learning Suite that I will show you. And you'll need to do these by 11:59 p.m., so just before midnight on the day of the lecture. If you'd like to work ahead on these and get far ahead, I am totally fine with that. Just don't get behind or your grade will suffer. Now, let me show you really fast where those are on Learning Suite. You'll see I have the student view pulled up here, so this is how you'll see it. If you go to your schedule, I've tried to put just about everything on this schedule for you. And you'll notice that you have a bunch of quizzes that you'll have to take during the semester. They mostly all open on August 26th. That way that you can do them early if you get to them early. But say you're taking lecture 1, you'll just click on the lecture 1 quiz. So these exams for the lectures and reading are really simple, right? They just ask you, did you watch the lecture and did you read the reading? there's an answer of yes, which will get you full credit, no, which will get you 0 points, and some of it, which is half credit. I'll let you decide where do you draw the line on some of it, whether you deserve half credit or full credit or none. I don't expect most of you to be terribly dishonest on this part. So with these quizzes, I have it set up so you can take them multiple times. So if you accidentally screw up, you can go back in, or you can always save and exit and start over. Let me show you now where your reading assignments are. If I go back to the schedule, you'll notice in this far left column, we have things associated with the lecture. So right here, I have read chapter 1, slides 1. So these are the slides for lecture 1. You don't necessarily need to download the slides, but they are there available for you if you want them. And then the video is right here. You can click on that, and that will lead you into a YouTube clip, and it'll take you to a video of this lecture we're watching right here. Trippy, right? As for the homework, we are using a third-party software program called Sapling. I have a link here in the lecture slides if you can't find it. This is online, so you'll need to register. This isn't something that we're doing new for these COVID-19 semesters. We've always just done it online. All of your homework assignments for a week are due on Saturday at 11:55 p.m. So this is the homework assignment associated with the lecture from Monday and the lecture from Wednesday. So you should have 2 assignments due every week around midnight on Saturday. I like homework to feel helpful rather than punitive. And so you actually will get an infinite number of tries on each homework assignment. I would love for everyone to get full credit on these. However, when you have infinite attempts on online homework, there's this strange phenomenon where people actually tend to take a little longer on the assignment than if they had a limited number of tries. And this is usually because you'll enter an answer and you think, oh, I got it wrong because I had a slight error. Then you'll try and fix it, and that won't give you the right answer. You'll keep doing that sometimes for 20, 30 minutes. I mean, you've probably all done something similar to that at some point, and if not, you will definitely this semester. So if you get stuck on a problem, don't try to work through it forever, right? If you spend more than an hour on a single homework assignment, that's probably way too long. There are some homework assignments or homework problems that take a little while longer, but most of them shouldn't take anywhere near an hour. So if you hit that hour mark, just put a pin in it and go get help from either me or the TAs. Now, if you put in your homework late, there's a 10% penalty per day. So if you answer, I think this is how it works, I could be wrong, but if you enter answers for 5 questions and get those wrong, but the homework assignment has a 6th question, it should only take off this 10% penalty for that question you didn't answer. And of course, all of the homework closes on the last day of class. So this is going to be a Thursday this semester, and then you have your reading day on Friday. Your homework is weighted as 11% of your final grade. I don't drop any assignments, so do try and keep up with that. Now you'll see I have the homework suite pulled up here at Sapling, and I have a link to this on the lecture slides. But this is basically what it looks like. There's some introductory stuff. So there's a video on how to use Sapling. You can watch that if you want. I've actually never even watched it, and I'm pretty sure only about 30% of my students do. However, there are these 2 practice assignments. So these are for points, but they should be easy. They're really just to help you understand how Sapling works. The second one right here, the chemical equations training, you definitely want to do that because like any software, entering chemical equations can be a bit of a pain. So Sapling is a good online homework suite, but like any of these, it's not perfect. And one of the biggest places I get complaints is in entering chemical equations. So do try and do that training and do a good job figuring out how it works. And then if you can't remember later in the course, either turn to this or ask me for help. So I have all your assignments listed right here, and they will have due dates over here once I'm done assigning those. And they are also listed on Learning Suite. On this left column in the schedule, you'll notice that you have your homework due dates listed. They're all going to be on Saturdays except for the very last one. These are not links to the sapling homework page. I probably should have made them links when I made this layout, but now I am too lazy to go back and fix it. So you'll just have to work around my laziness. As for lab work, there will be a total of 8 labs in this class, plus an Excel spreadsheet training. 2 of the labs will be moved online after Thanksgiving, and so there's going to be a little bit of rearrangement there. The labs 6 and 7 have been moved to after Thanksgiving, and lab 8 has been moved up. So you'll notice we're doing them a little bit out of order. Again, this should be fine. It shouldn't actually cause us to have any cognitive disconnect. All the information should be available, and we should be able to get through that just fine. The criteria for how I will grade each lab is listed online. And for each lab, you're supposed to read the labs or the lab procedures and watch the lab videos before coming to lab, and take the associated lab quiz before coming to the lab. And I will show you really fast where to find all of that material. Okay, all of the lab material is in this middle column on the schedule page on Learning Suite. Okay, you have on our first day of lab, we will be having lab. We'll be doing a lab orientation and basic training, and we'll be doing checking in to lockers, etc. And there will be a safety video associated with the lab. You'll need to watch this video, and then there's a safety quiz that you need to have done by Friday, the first week of class. That would be Friday, September 4th. So this quiz, you're required to get 100% on it. You can retake it as many times as you want, but you have to get 100% on it, okay? And then for lab 0, we'll have our spreadsheet training. You'll notice that there is a Excel spreadsheet right here where you'll download that. And that'll walk you through how to use Excel. And we'll get into that in a later lecture, and then there will be a video here associated with that lab. And then as we scroll down, our first lab doesn't actually start till September 14th, but you'll notice here with lab 1, there's the procedures. You'll need to read those before coming to class. There's the lab 1 report. This is an Excel spreadsheet. The majority of the lab reports in this class, or rather all of the lab reports in this class, will be written out in Excel spreadsheets, so it's a good idea to bring your laptop with you to class if you have one. And then the lab 1 video, this actually goes over the procedures and actually shows how I do the experiments. It is not, they're not very long. I think the longest is about 15 or 20 minutes. You need to watch all of these before coming to class, and then take this lab 1 quiz, okay? This quiz is going to be very similar to the reading quizzes. I will come in here and open up the lab 1 quiz if I can find it, okay? So this just asks, did you read the procedures and did you watch the videos for lab 1? Okay, now whether you want to bring the physical procedures with you and print them out and off of here and bring them with you to lab, or write them out in a notebook, it is your choice. We are not grading lab notebooks in this class, but you will need to turn in your report, and you'll need to know how to do the lab while you're in there. So I generally recommend just printing out the procedures, this document right here, read through it, take the quiz, and then come to class with your laptop ready to do the lab. Now, all of your reports for the labs will be due Friday at 11:59 p.m. You'll submit those through Learning Suite. If you go to Home, Assignments, you'll notice that in here you have your lab quizzes and your lab reports. And next to the lab reports, there's this rubric button. It'll give you a breakdown of how the lab is graded. You can read through those to figure out exactly what I'm looking for. And for each lab report, I actually only look at the report page, but we can get into that a little bit more. and then you'll just hit the submit button here. You'll upload a file. It'll look slightly different for you than it does for me. It'll give you a spot to upload a file. If you upload the wrong thing, you can always re-upload it later. Now, all of these labs are going to be due Friday at 11:59 p.m. You'll notice that I put the due dates for the lab on Friday and the due dates for the homework on Saturday. And this is to help those of you that are severe procrastinators that won't start an assignment until an hour before it's due. This way you don't have 3 assignments all due at the same night. You have 1 due on Friday and 2 due on Saturday. These will be weighted as about 53% of your final grade, and you need to complete all of the labs in the class to pass, so you can't skip any of them. And again, those are slightly out of order. Now, something I didn't include on this slide, but what we'll go through a bit in the lab, is there will also be lab groups. Usually for the lab, you work with other students in the lab collaboratively. However, to maintain social distancing, I am going to have you try and work together on Zoom. You'll come up with a meeting time with your group. I will assign you a group, but you'll come up with a meeting time, and you'll need to meet with your group once a week. And we'll talk a little bit more about that once we get into lab. So don't worry too much about that just yet. Finally, exams. There will be 3 exams in this class. They're weighted as about 1/3 of your final grade. Those will all be administered online through Learning Suite. You'll have a 3-hour time limit. So I was administering these exams through Learning Suite before everything went online. So I'm pretty happy with the way this works. Average time on these exams is between 1.5 hours and 2 hours. So 3 hours is generally plenty of time. And when you're taking the exams, you can use Excel for calculations. So the first 2 exams will each be worth 100 points. Exam 1 will cover lectures 1 through 9. Exam 2 will cover lectures 10 through 11 and 14 through 18. The reason that we're not covering 12 and 13 here is because we had to move 12 and 13 to later in the semester due to our rearrangement of the lab schedule. And so the final exam will be worth 150 points. 2/3 of that will cover lectures 12 through 13 and 19 through 23. So we'll have about 100 points dedicated just to those lectures. And then the last 1/3 of the exam will be cumulative. And there is a study guide and equation sheet for you online on Learning Suite. Let me show you where those are at really fast. If we go over here to content under exam material, you'll notice here are our equation sheet and our review topics. You'll want to pay attention to the review topics document, as that will really go over what's really critical for you to learn in this semester. I've tried to revamp the homework assignments to more directly correlate with that. I think I've done an okay job, but you'll notice that 1 or 2 homework assignments still have some questions that aren't really covered on that. But the exams will mostly focus on material on this review topics document. And by mostly, I mean it will completely focus on that. You'll also notice that under lecture materials, I also have all the materials for the lectures listed in here as well. And under lab materials, I also have all the materials for the labs listed in here. Last, let's talk about office hours. So initially, when we were moving things around, I didn't plan on this being labeled a mixed class or whatever it's called. I was hoping to still have a scheduled lecture time, and I was going to use that lecture time essentially as office hours. So I'm still going to try and have my office hours on Monday, Wednesday from 1 to 2. So this will be right before the lab. Hopefully a good amount of you still have that time available. If you do, I recommend using that to watch your lectures, etc. And then you can just come into the Zoom meeting and ask questions when you need it. I also try to be fairly accommodating with various schedules. And so if you can't make my office hours and you need to pester me all the time, at other times that's totally fine. email is the best way to set up different office hours with me, because then I'm most likely to remember that we set up other office hours. I'm generally going to try and hold office hours by Zoom, so this actually works fairly well. I'm able to draw on the Zoom screen to answer questions and so forth. My meeting ID is listed right here. I'll probably post this somewhere on Learning Suite, but I don't know where to do that just yet, so hold on for that. My password for all my Zoom meetings is Zebra, just because it's easy to remember. And of course, here's my email, and this is also listed on Learning Suite. Now, let's go ahead and get into some actual review topics. And for this, I will pass it back to Dr. Mortensen from the past. That covers the structure of the class. Now we're going to go over a couple of topics that you'll need to know for the class. The first one is serial dilutions. It also includes a little bit of washing glassware. I start with a flask, and it has 1 liter of a 2 molar sodium chloride solution. So this is pretty salty. The Great Salt Lake actually only has a salt solution. The Great Salt Lake actually only has a concentration of about 0.46 molar sodium chloride. So this is way saltier than Salt Lake. Let's say now we dump this solution out and there's just some drops left at the bottom. Let's say there's only about 1 ml remaining at the bottom for convenience. And then we do 1 rinse of this guy with 500 mils of water, and we dump that all out. Now there's just 1 liter down here remaining. What's the concentration of that? Well, it's 0.004 molar. You can still taste that. So here we dumped out this salt solution, we rinsed it 1 time with water, and now this remaining stuff down here has a concentration that is still salty enough to taste. So let's try this again, but instead of rinsing with 1 douse of 500 mils, let's rinse it 3 times with 100 mils each time. So again, we're starting with this 2 molar sodium chloride solution. We've dumped it out. There's 1 milliliter left down at the bottom. Then we rinse with 100 mils of pure water. Well, after that first rinse, we've now dropped the concentration down by a factor of 100. So now it's 0.02 molar. We rinse it again with 100 mils of water. We've dropped that down now to 0.002 molar. And this is now below your taste limits, or below most people's taste limits. And if we rinse it a 3rd time, drop that concentration of this 1 milliliter droplet down here by another factor of 100, now we're at 0.000002 molar. So if we compare this value to the value that we got when we rinsed 1 time with 500 mils, you'll notice that now we're 20,000 times more dilute than we were, even though in this case, we only used a total of 300 mils of water to rinse this guy out, whereas before we used 500 mils to rinse it out. So the takeaway here is that you can get down, or you can get your concentration down much more quickly by doing serial dilutions with small volumes than you can by doing a single dilution with 1 volume. A practical application of this too in the lab is that it's better to rinse a bunch of times with small amounts of water than to just fill your glassware with a bunch of water 1 time. And of course, you're not going to be rinsing glassware, but I generally make a point to my students to not leave DI water running into your glassware to get it clean. And this is for 2 reasons. One is that it wastes a lot of DI water, and we have to pay for that. It's not an astronomical cost that we're not willing to pay for using for normal glass or for normal lab use. But the second reason is because as the water comes in here and fills this guy up, your water actually just hits here and spills right out the top and doesn't mix down in here. So even if you're leaving your water running into your glassware, you're not really changing the concentration at the bottom of your glassware very much. And so just rinsing for a long period of time with running water doesn't usually do you very much. Okay, so I've kind of introduced serial dilutions, and to figure out these new concentrations, I had to use an equation. This equation right here, C1V1 equals C2V2. Now this is an equation you should have seen previously in Chem 105 or 106, but all this means is that the concentration times volume of your starting solution is equal to your concentration times volume of your ending solution. And this, of course, is an equation we use when we're diluting solutions or when we're concentrating them sometimes too. So right now, I have a beaker full of analyte solution. The concentration of my analyte is 25 millimolar. I have a graduated cylinder that goes up to 100 mils. And I have unlimited plastic pipettes and unlimited DI water. What I want to do is to make a 100 mil solution that has a concentration of 10 millimolar of my aqueous analyte. So the question is, how much analyte solution do I need to add, and how much water do I need to add? Go ahead and pause the video right now and see if you can't work this out by yourself. And then once we come back from being paused, I'll work through the solution. So go ahead and pause. Okay, here's how you should do this problem. So we have C1V1 equals C2V2, and we can plug in values that were given in the question into that equation. Our starting concentration is 25 millimolar. So we put that in for our C1. What is our V1? Well, we actually don't know V1. That's what we're trying to solve for. You might think it's the volume in your beaker, but it's not. It's the volume you take from here and add to your graduated cylinder. That's what we're trying to solve. We know that our final concentration, we want it to be 10 millimolar, and we know our final volume, we want to be 100 milliliters. So then we just rearrange this equation and solve for V1. That just looks like this. We plug those numbers into our calculator, and we get a value of 40 mils for our analyte solution. The next question was, how much water do we need to add? And for this one, we don't have to do a lot of fancy math. We know that we're trying to make a 100 mil solution. We know that we added 40 mils of our analyte, so that last 60 mils has to come from water. So that's just subtraction. Okay, so this is a straightforward problem, but in analytical chemistry, we actually don't use graduated cylinders very much. We actually tend to use glassware that looks like this. What I'm showing here is a 10 mil volumetric pipette. So this is calibrated very precisely to where this red line right here, I don't know how well you can see that in the video, but there's a red line right here. And if you fill up to there, then you get exactly 10 mils of solution. Over here, what I'm showing is 200 mil volumetric flasks. So these are similar to the pipettes, except these, of course, you don't suck solution up into, you put the solution into it. And these also have little graduated lines right here, right here. And if you fill up to that line, then you have 100 milliliters of solution. We often also use plastic pipettes, but we don't measure anything with them. We can use those to add water to these volumetric flasks until we get up to that 100 mil line. Okay, here's another practice problem for you though. With this glassware, how do we go from a 25 millimolar analyte solution to a 0.5 millimolar analyte solution? Go ahead and pause the video right now and see if you can't figure out a method for doing this. Here's how we would do it. We would first take our 10 mil volumetric pipette. We would take 2 aliquots of our analyte solution and put them over here into our volumetric flask. We would then take water using these pipettes over here and fill our volumetric flask up to the 100 mil mark right there. This will give us a final volume in this container of 100 mils and a final concentration of 5 millimolar. Right, so we've gone from 25 millimolar now to 5 millimolar. Let me know if you have questions about that. The next step that we would do is from this solution that has 5 millimolar in it, we would take one more aliquot of that and put it in this other volumetric flask, which is behind my words over here. And then we would fill the rest of this guy up with water. So we moved 10 mils of 5 millimolar over here. We diluted it with water up to the 100 mil mark, which is right about here. So now our final volume is 100 mils, and our final concentration is 0.5 millimolar, which is exactly what we want. Let me know if you have any questions about that. You might remember this equation right here for K, where K, our equilibrium constant, is equal to the concentration of our products raised to the power of whatever coefficient is in front of them in the equation, divided by the concentration of our reactants raised to the power of the coefficient in front of them. Some rules for equilibrium constants. All of our solutes are listed in moles per liter, so that's anything dissolved in a solution. Any gases are recorded in bars, and pure solids, pure liquids, and solvents are omitted from the equation. So we don't include, for example, water in this equation. Or if one of our reactants or products is a solid, we wouldn't include that in there either. Okay, so let's practice with this a little bit. I have this equation right here where zinc is reacting with ammonium to give us zinc 2 plus hydrogen gas and ammonia. So let's write the equilibrium constant for this reaction. We get this, where K is equal to the concentration of the zinc 2 plus ions times the pressure of the hydrogen gas in bar times the concentration of ammonia raised to the second power, because ammonia has a 2 coefficient in front of it there. And then on the bottom, you'll notice we didn't put zinc down here. Why? Why did we not include zinc as a reactant in this equation? The answer is because zinc is a solid, and solids don't go into equilibrium constants. So we just have the ammonium ion concentration on the bottom here raised to the second power because of this 2 coefficient in the equation. Now with equilibrium constants, let's review our acid-base dissociation constants. So if you'll remember, an acid generally has this equation when put in water. So you have your acid with a proton that reacts with water and gives up a proton and gives us this H3O plus complex, or you can also write this just as H plus a negatively charged conjugate base. So our equilibrium constant for this reaction looks like this. Ka is equal to the concentration of our conjugate base times the concentration of H3O plus divided by the concentration of our acid. Or it can also be written like this. This equation right here is the exact same as this, except that H3O plus has been changed to H plus. The reason we sometimes write this as H plus and sometimes as H3O plus, because it's generally believed that this free proton forms a complex with water and sticks to it. But functionally, these two equations are identical. And then for bases, we have our base equation in water. So a base, as you'll remember, steals a proton from water. And so our base will react with water to form BH plus OH minus. So then our base dissociation constant, Kb, is just equal to Hb plus times OH minus concentration divided by the concentration of our base. If you have any questions about that, let me know. And of course, these are both used for weak acids and bases, which we'll review later in the semester too. Then the last equilibrium constant we need to talk about today is Kw. So Kw, of course, is the auto dissociation constant of water that describes how much H plus and OH minus are in water. And we can derive this actually from the equations for acids and bases. Let me show you how we do that to start with. So if we start with the equation for an acid and the equation for a base, and we line these up, now you'll notice, of course, I changed my notation here for the base to be A instead of B. So this is A minus, so we're actually using the conjugate base of our acid up here. But if we combine these two equations and add them together, then some of the things cancel out. So HA is going to cancel out on either side. A minus is going to cancel out on either side. And we're going to be left over with water on the left for both reactions. So if we add those together, we get 2 waters. We'll still have our H3O plus and our OH minus. And this is the equation then that describes the autoionization of water. So what does KW actually look like from these? Well, since we're adding these 2 equations together, we actually have to multiply their K values together. So KW then is equal to Ka times Kb. Ka, of course, is equal to A minus concentration times H plus concentration over HA. Kb is equal to HA concentration times OH minus concentration over A minus. Of course, HA here will cancel out, the A minuses will cancel out, and we're just left with H plus and OH minus. Now, you don't necessarily have to remember this whole derivation or this one up here. It's important that you understand where it comes from, but you don't necessarily need to memorize the derivation. But you do absolutely need to know this relationship, that KW is equal to Ka times Kb. And that's going to be very important throughout the semester. Now let's review some other factors associated with K values. So let's say I have 2 reactions. I have this reaction up here where A plus B is going to C plus D, and this one where W plus X is going to Y plus Z. The K value for reaction 1 is 26,000, and the K value for reaction 2 is 12. The question I pose to you then is, which reaction reaches equilibrium more quickly, reaction 1 or reaction 2? Think about that for a moment. You can pause the video if you want. The answer, of course, here is we don't have enough information. Just knowing the equilibrium constant doesn't give us any idea of how quickly it reaches that equilibrium constant. It could take days or months or years or seconds or microseconds or nanoseconds. That time scale doesn't actually affect these K values. It's not reflected in them at all. Another factor we need to review is a value similar to K, known as Q. So the equation for Q looks identical to the equation for K, but functionally these 2 equations are different. The way that they are different is K describes our reaction at equilibrium, Q describes it before it's at equilibrium. So K here is a constant, Q varies depending on what time you're looking at in your reaction. So if you just first throw A and B together, you're going to have 0 C and D in there, and so your Q value will be 0. If you wait forever until this reaches equilibrium, then Q is going to be equal to K. Okay? But if your Q value is greater than K, which direction will this reaction move in? So let's think about this. Q is greater than K. To increase the value for Q, we have to increase the amount of products, decrease the amount of reactants. Of course, if this has more products than it would at equilibrium, then those products are then going to react to give us more reactants. And so it's going to shift this reaction to the left. If you have questions about that, feel free to reach out to me. This, of course, gets us into Le Chatelier's principle. If you remember, what Le Chatelier's principle says is if you add some to the left, you'll shift the reaction to the right. If you add some to the right, you'll shift the reaction to the left. But it gets a little trickier than that in practice, and let me give you some questions to help you identify why that gets a little more tricky. If we add equal moles of B and C to this reaction, which way will the reaction shift? Well, there's 3 moles on the C here, and there's 1 on the B here. So does that mean we have to add 3 times as many C to cancel out the number of B? Or does that mean that 1 mole of C is 3 times more than B? Well, actually, the question doesn't even require us to think that way. The reason is because B here is a solid. Because B is a solid, it's actually not going to factor into our equilibrium constant. And Le Chatelier's principle is actually only associated with affecting the equilibrium of our reaction. So we change Q, and then Q tries to get back to K. So if you add equal moles of B and C, this is going to shift to the left because B is a solid, doesn't show up in our equilibrium constant, but C is an aqueous species, does show up there. So if you add more to the left here, we're going to shift, or sorry, if we add more to the right here, we're going to shift the reaction to the left. Next question. If the size of the reaction vessel is doubled, in which direction will the reaction shift? Okay, for this question, we have to think, what does doubling the reaction vessel size do? I didn't say we're doubling the quantity of products or reactants present. We're keeping those exactly the same. So you can think if this reaction here is happening inside a plunger or inside a syringe, and we pull the plunger of the syringe back, which way do we shift the reaction? Well, is changing the volume going to change what a solid is doing? No. Is it going to change what aqueous species are doing? No, it's not. They're still going to be inside their liquid, and the liquid has a fixed volume. The thing that doesn't have a fixed volume is a gas. So as we pull back on that plunger, we're going to increase the volume of course, our gas is going to have some sort of equilibrium partial pressure that it's going to try and achieve. So if we increase the volume here, we're going to shift this to the right because we're going to want to produce more gas to balance that out. The last things we're going to cover today are SI units. You should remember what most of these are. You might not remember the values of them, but you should review these tables. These are found in your book in chapter 1, I believe. And you should remember that length and mass and time are measured in specific units. You should be able to recognize all of these SI units. So we're not going to go over them in detail in the lecture because I think that you can mostly just review them in the book and that'll be sufficient. You should also be familiar with the prefixes we add to SI units, such as kilo, centa, milli, micro, etc. I've highlighted here the ones that we use most often. You don't necessarily have to remember iota and zeta and so forth, but you should be able to understand where to look those up if you need them. And again, we won't be reviewing these on the lecture today, but you should make sure to refamiliarize yourself with any of them if you've forgotten them. You'll also need to remember how to do unit conversion, and you'll need to be familiar with these other common units that are derived from base SI units here. So I have their base SI units listed here. I have their values listed in other SI units here. And of course, their symbols. So things you need to know are things like frequency, force, pressure, etc. And again, these are things that I think you can review on your own. So that does it for lecture 1. Feel free to reach out to me with any questions, especially if you're having trouble finding out how to register for SAPLab.